Welcome to the Business Value of Computational and Generative Design for Executives presentation. My name is Emily Bisaga Dunne, and I'm the Industry Outcomes Lead for Building Design at Autodesk. Follow me on Twitter, @DunneDesignTech. My perspective on building design comes from a broad and architecture-focused background. I was previously the architecture technical evangelist at Autodesk in the Business Strategy and Marketing Group, as well as a premium support specialist for enterprise priority accounts and a consultant for generative design and BIM. I've been at Autodesk for about 3 years now, and I've been really fortunate to work with some amazing people to envision business strategy, outcomes, and processes for technology adoption, and also to usher the AEC industry into the next generation of design technology. I've also worked for CBT Architects as a design technologist, at Mulvaney G2 Architects as an architectural designer, and at Choi Kobus & Associates as an interior designer. I have several years of experience working in the AEC industry on a variety of building typologies, from retail to multifamily development, and throughout all phases of design. I attended CUA, RISD, and BLS, earning my Master of Architecture degree, concentration in real estate development, Bachelor of Interior Architecture, and Bachelor of Fine Arts degrees. I wanted to take a moment to say thank you to my incredible colleagues, Kyle, Mike, Zach, Lily, Jacob, and also Dieter. I'm really proud to work alongside these individuals. Their contributions and review of the material are critical to the success of this presentation. Also, the book Architecture Design Data by Phil Bernstein has been a highly valuable resource in shaping the foundation of value study of design in this presentation, and I highly recommend purchasing and reading that book. You should walk away from this presentation with a complete understanding of the business value of computational and generative design. We'll review a shifting design strategy paradigm in the context of these emerging design processes, and also understand how to implement them in a project, as well as sell them to internal and external stakeholders for adoption. At Autodesk, we're making tools to help you with design challenges every day to make anything. For the AEC industry, we're working to strengthen the intersections of processes, collaborators, and technologies for building design. To really understand the business value of computational and generative design, let's start by looking at the evolution of ideation in architecture. Traditionally, a building design in architecture was expressed as a single idea, or a partie, meaning the departure point or grand driving idea in a design. Buildings have traditionally been conceived from very broad ideas and sketches, and then refined into the final form. The most basic way we've had historically to express our ideas is with simple lines and forms grounded in reality, such as lines in the soil or sand, arrangements of stone and earth, or charcoal sketches in caves like Lascaux. With this expression, we're able to convey a wide array of ideas at specific sites, but these ideas were subject to erosion with exposure in the elements, so we turned to a more easily protected medium that allowed for off-site and also mobile expression: paper. With the advent of paper, our ability to ideate expanded into sketches, technical drawings, perspectival renderings, paintings, and we were able to protect our ideas. However, we're not able to easily make changes to our drawings or demonstrate ideas consistently. And so, with the advent of computing technology, we're able to harness the power of application development to translate the manual process of ideation into a digital space. One where we're able to replicate our previous methods of mark making, with added benefits such as consistent legibility of line weights and repeatable design elements. Moving ideation into the digital space did, however, have a certain degree of drawbacks. Collaborating on ideas was difficult. Model making and drawing, they're still separate processes. And any insights were generally done as manual calculations and then recorded and manually input schedules. And so we needed a more robust, integrated process for ideation. And this is where BIM has stepped in to help us to unite our efforts in expressing ideas in models and drawings. BIM, short for Building Information Modeling, was and is really a radical shift in the evolution of ideation, placing all ideas and expressions of those ideas in the same place and creating a single source of truth for ideas. With BIM, we're able to model and draw simultaneously, as well as perform integrated analysis and calculations, while automating views, schedules, and renderings, and we're able to make updates quickly and easily with parametric elements in the BIM model. With the advent of BIM, we're seeing exponential growth in the next generation of ideation evolution. We're simultaneously seeing innovations in cloud computing, hardware and software capabilities, and artificial intelligence. With these innovations, tools for ideation are evolving to include immersive visualization, enhanced collaboration, automation of design processes, optimization of designs through option generation, and predictive assistance in achieving design goals and project outcomes. So these new ways of working will help us spend less time occupied in repetitive tasks and tedious design option exploration. As complexity of designs are growing, while timelines are becoming shorter. Computational and generative design are critical ingredients in the recipe for more efficient building design workflows. Computational design is a term to describe the capability to automate processes, from basic repetitive tasks to geometry creation. Generative design is the term used to describe the capability to optimize processes. Utilizing design option generation and evaluation tools to validate designs. These are the two emerging ways of designing that we'll focus on in the context of strategy, adding value, and winning more work. This first diagram shows a basic workflow for developing a conceptual tower mass in Revit with BIM capabilities. It's possible to craft the design concept in a building mass in Revit, then assign parametric constraints that allow the building mass to flex. And when the final design is decided on, the idea may then be documented in the Revit environment. This workflow allows you to test ideas with flexibility, but does not allow you to keep a record of options as you're flexing your designs. And if you need to create the study again, you would need to craft this in a future project environment. This second diagram shows a basic workflow for developing a conceptual tower mass in Revit with BIM capabilities and the integration of computational design. Rather than crafting the design concept in a building mass in Revit, this study uses the site boundaries and a series of rules for geometry development based on the site and project constraints to automate the geometry in Dynamo. Dynamo is also used as an evaluation tool where you're able to flex the design and review options like you could in the parametric environment in Revit. But again, does not allow you to keep a record of options as you're flexing your designs. When the final design is decided on, the idea may then be transferred from the Dynamo environment into Revit and documented in the Revit environment. The major benefit of Dynamo is that if you need to create the study again, you may now automate the process entirely in a future project environment. This third diagram shows a basic workflow for developing a conceptual tower mass in Revit with BIM capabilities and the integration of computational and generative design. Similar to our previous example, this study uses the site boundaries and a series of rules for geometry development based on the site and project constraints to automate the geometry in Dynamo. Rather than evaluate the design options one by one, as we did previously, Refinery allows you to create a study that shows a series of options and allows you to keep a record of your options to review with your stakeholders. You're also able to filter based on design criteria and design goals to discover the optimal design solution. When the final design is decided on, the idea may then be transferred from the Refinery environment to Dynamo and into Revit for documentation. The major benefits of this workflow are the ability to automate the generation of geometry, automate the generation of design options, and maintain a record of informed decisions. Let's talk now on a higher level about project strategy. When designing with what I'll refer to as a traditional project strategy, business leaders within a company are typically kicking off projects with a small circle of stakeholders to identify the project type, some of the big ideas for development, and think about the type of processes that might be used to complete the design work. The design process is a mix of proactive and reactive work, where ideas are produced in charrettes, reviewed in critiques, and often result in sequences of revelations during the iterative portion of the design process. Following iteration, construction is completed, as-builts are delivered, and the project is closed out. Design teams rapidly move on to the next project. In traditional project strategy, the method for developing design options is a little bit like a game of Battleship. Ideas are tested one at a time, often without enough information to get a hit the first time. We ask ourselves, does this work? What about this? We might get a hit, or we might get a miss. Oftentimes, only a few designs can really be evaluated because the design team runs out of money or time, and the evaluation process can be frustrating, as goals may not be clearly defined to even test against. Design strategy generally can be thought of as a funnel. We start in a wide open space of ideas, and throughout the entire process of designing, ideas are constrained. This may be accomplished through a siloed traditional design strategy, with a charrette critique and craft approach, requiring heavy amounts of manual processes to complete the building design. Or this may be accomplished with a more contemporary design strategy, where building designers are deploying a mix of manual, digital, and automated processes to complete the project more collaboratively in the ever-narrowing idea funnel of the design process. You've probably seen the McLeamy curve at one point in time in a presentation talking about design project strategy. This diagram clarifies where we are able to impact the cost and functional capabilities of a building design project based on what tools we're using in our project strategy. You can see that in the traditional design workflow, most of our effort is spent in the construction documentation process, chasing updates across drawings and coordinating the symphony that is a CD set. With the advent of building information modeling and parametric technologies, we've seen a shift in the graph to the left, and we're now spending more effort in the schematic design and design development phases of the project. As the project progresses and more decisions are made, the elements of the building are constructed, the cost of design changes increase exponentially. The future of project strategy has been heavily influenced by the capabilities of computational and generative design. In order to automate and optimize workflows in the development phase of the design process, a rigorous and extensive discovery process of project and design goals and constraints is required. The design process is then largely proactive, yet flexible, providing the opportunity for downstream ideas to inform upstream development framework, and for specialists to have more and more meaningful conversations, informing design outcomes at any stage of the process. Beyond simply creating buildings, the future of building strategy is expanding into capturing insights from the building's life cycle, to close the loop between design and execution, and also reality, and using the same data to inform future building typologies, leading to growth opportunity for strategy adopters. We're calling the next evolution of design strategy outcome-driven design. And we're defining this as a focus on value-driven design and construction with democratized collaboration for enhanced building performance, process efficiency, and realized aligned outcomes. One noticeable difference between our previous strategies and this new strategy is that there's a wider funnel at the outset of work, and that we've expanded our opportunities beyond that of building design into lifecycle management, data aggregation and analysis, and project typology data curation. With the introduction of outcome-driven design, we can see that the effort put into a building design project is shifting significantly into the pre-design and schematic design phases, and that our ability to design with flexible parametric models, informed by computational and generative design toolsets, allows us to impact cost and functional capabilities later and later on in the design process. As an architectural project is difficult to change once it's built, but using flexible modeling tools, designers can delay finalizing decisions until the model is baked. With the design effort shifted forward, we have opportunities to improve our visualization capabilities by adopting emerging workflows such as Revit and Unity Reflect, pour more time into researching and resourcing local and sustainable materials and systems, and review performance data in Insight, as well as spend more time researching and digging into detailing on the project. Beyond the traditional design duties, when we implement an approach to design that maintains our relationship with the client throughout the operations of the building, this allows for the curation of the building performance data through advanced analytics. And then we have opportunities to point out where design for the building could advance into a new scope of work or a new system specification. Also, everything that we learn about how the building is actually performing versus how we expected the building to perform can be integrated into a building database by typology and used to inform the future of your building design with predictive analytics. Now is the time to prepare your data for the emergence of artificial intelligence technologies. In outcome-driven design, there are 5 key components. With strategic planning, the goal is to align all upstream and downstream stakeholders to identify what everyone needs up front to ensure project success. With outcome-driven design, goals and constraints drive the development of form and order in the building information model, with an emphasis on building performance. With parenthetical analysis, there's an ongoing dashboard of all of the big picture project aspects, like counts, costs, energy analysis, etc., that give the designer the ability to pivot and course correct the project in real time. With integrated project delivery, we're collaborating in an integrated way that will allow for fast and seamless transfer of data between projects. And with operational nurture, we're extending the scope of our services beyond that of traditional architecture and into customer success, seeing the building through its life cycle process and acting as trusted advisors to our clients. So what? Why is this important? And most importantly, what is the business opportunity? This is important because our industry has a lot of trouble demonstrating value. This is a funny way to look at the idea that perception is reality. How do our building design clients perceive our value? How does the industry perceive the value of building designers? Let's take a look at architects' salaries as compared to lawyers. Maybe we should have thought about studying law. There's clearly a scarcity of architects in comparison to lawyers, yet the wage gap is vast and grows wider as the 2 career paths diverge from starting salaries. It looks like there's generally a failure among architects to convert the value of services into profit. Phil Bernstein sums this up well in his recent book, Architecture Design Data, where he talks about what is going wrong in terms of fees and our ability to demonstrate value. And I quote, "If architects are a relatively rare commodity which normally drives up prices, and delivers such important service to society by creating all of the buildings that it needs to function, why have we done such a poor job of converting the clear value we deliver into an understanding by clients and the public, and, as a desirable consequence, getting paid accordingly?" On top of this disconnect, we're operating with a stagnating architectural billing index in an uncertain market. And recently, in the US, we're experiencing some billing index woes. The frustrating part of this is that architects' fees are such a relatively small part, 10%, of the total design and construction costs for a building, and 0.01% of the total building lifecycle costs. It would only take a fraction of the cost of the overall design and construction costs of a building to increase our fees. But this is really very rarely the reality. And we're working amid a really disincentivizing compensation system. The vast majority of work comes in as lump sum or fixed fee payment structure. We're seeing a lot of difficulty in negotiating for higher sums at the onset of a project for building design teams in this fee structure. Margins are tight and competition's fierce, and it's easy for competitors to underbid. And in researching the topic of payment structures, I've been hearing worse feedback on rates from architects working on an hourly basis or otherwise. Not only is the difficulty in negotiating hurting us, but also in the lump sum fixed fee structure, we're seeing the risk transferred onto the building design team for work completed. And we're working with a client who may not have any special consideration for the process by which we work. So if something is fundamentally critical for our industry to implement in our projects, such as sustainable design practices, may be easily disregarded by all parties. Because even the architect and downstream building design team do not have incentive to necessarily work harder or implement emerging capabilities in this fee structure. Less time spent on work means less salary paid and more profit, technically. And if you felt comfortable with your abilities in your previous workflows, even if they were manual and crafted and possibly outdated, why would you change your process? One very compelling reason to make a change is that, generally, our buildings are not performing well. They're pretty inefficient, and our construction processes are also pretty antiquated and chaotic. Our buildings are responsible for consuming 40% of global energy, consuming 25% of global water, and contributing around 30% of all global GHG emissions. Beyond any political arguments around the matter, our buildings are simply not performing as well as they could be. We're not meeting sustainable design requirements as an industry, and it's clear that our industry needs to change if we're going to meet the upcoming demand for buildings based on population growth. That's not just a change in how we construct our buildings, but how we design them. Even the AIA Code of Ethics has changed to include language on sustainability. Quote, members should select and use building materials to minimize exposure to toxins and pollutants in the environment, and to promote environmental and human health, and to reduce waste and pollution. It's not just about health, safety, and welfare of people. It's also about the health, safety, and welfare of the environment. But here's the thing. We know that our work, when done well, reduces costs, improves timelines, and fosters community development and wellness. And we clearly didn't go into this for the money, so I'm fairly certain that everyone's heart is in the right place when it comes to designing buildings. We do perform an extreme scope of services during the life of a design project. And we also orchestrate an extreme scope of consulting services. So, at the end of the day, the problems we face in terms of value and compensation are due to process and perception. So, how do we fix this? We have 3 opportunities: to negotiate harder, to work smarter, and to figure out how to add more value with our work. The first item is tough. Like I said, there are very, very tight margins you can operate in with negotiation before you'd lose to the next offer. So let's skip to these highlights. We do have immense opportunity for working more efficiently with our emerging computational and generative design technologies. We also have the opportunity or challenge to offer new product lines and services. So the question to ask yourself is, what do I start with first? What if you could use outcome-driven design to impact both efficiency and value? Are you ready to revisit your business model? Looking again at our outcome-driven design strategy, we're able to overlay our tactics for adjusting perception and process by adding value and adding efficiency at various stages in the building design process. With the emergence of strategic planning services, live performance metrics, and operational services, we're able to add value, increasing revenue, and even offering a subscription model on building data management and insights for our clients. With the emergence of outcome-driven design and integrated delivery, we're able to set clear targets and expand the amount of work we're able to do exponentially in significantly smaller amounts of time to increase efficiency and reduce operating costs for design firms as well as clients when completing the design of a building. With all 5 of these components in place, we're able to increase our project success rates and win new work. With the implementation of this strategy, we're going to see several new roles emerge. A design strategist will be critical in the strategic planning phases of work, where skills such as Luma training and soft skills guide the gleaning of project requirements from key stakeholders. The design strategist will work closely with the design analyst and the outcome-driven design team to ensure that the value captured from clients turns into measurable metrics that drive design and are tracked and analyzed throughout the project. A design technologist is one part of the design technology team that will ensure that all design processes are optimized for efficiency for building design. The design analyst will be a new role that operates as the air traffic controller for ongoing projects and will track performance metrics as the design develops, flagging aspects of the model as they overperform or go off the rails, and ensure that the project team is aware and able to pivot for project success. The delivery technologist works closely with the design technology team and ensures that collaboration capabilities are utilized and functioning properly for federated models. The building design outcomes lead is the main interface between the company and the client during the operational phase of the building and ensures that the building operates as expected, provides insight into emerging systems and technologies to implement, and discovers new scopes of work based on usage. Ultimately, the building design outcomes lead is responsible for ensuring customer success, anticipating needs, and maintaining a long-term relationship with the client. For the sake of our focus on the business value of computational and generative design, let's drill down into the design technologist and the design technology team. These are the key players for the future of design technology. They will all be able to concentrate, recognize patterns and moves ahead, synthesize combinations, connect field experience with abstract logic, and capture datasets required for abstract logic development. The CTO acts as the strategist and liaison for the design technology team to executive staff within the company. The design technologist role is to look at emerging technologies in a broad way and vet the application of tech for usage in projects. The BIM manager role is to develop and ensure that all projects in the company are using the same template, data standards, and model management practices. The computational designer role is for a specialist with extensive coding knowledge to develop graphs that automate tedious processes for the company. The generative designer has a role that is part technical and part analytical, and requires the ability to move back and forth between strategic planning, value discovery, performance metric alignment, process implementation, and review. In a very small business, one person may act in all of these roles. But given the levels of development in each arena, I would strongly recommend filling these 5 roles as part of every technology team to ensure that your company is at the front end of the outcome-driven design adoption wave. For buildings, traditionally we're looking at a 7-phase process with a variety of stakeholders per phase, and a series of capabilities that are required to see the project through to completion. Your design technology team should be able to come in at any phase of the project and area of capability to make an impact on process efficiency. These are some examples where design technology teams have already been making an impact on efficiency and performance at various points in the project timeline. Whether optimizing building forms based on view opportunities, glazing, or cost, or ensuring that desks are laid out the best possible way, computational and generative design are making process automation and optimization possible and integral to the design process. To get started with computational design, the tool to use is Dynamo, Autodesk's premier computational design tool. With Dynamo, you can save time by automating processes and model more sophisticated design geometry using simple data, logic, and analysis. With Dynamo, changes and updates to projects become exponentially easier and more time efficient. In this example, we're looking at an early stage design study with an objective of automating the building mass and cost. This example shows testing a variety of variables for a rectilinear massing model to optimize the tower ROI, or return on investment, by way of Dynamo for the key outcomes of reduced time to design development, increased early stage design profit, and improved cash flow management. You can see that it's possible to flex parameters with sliders in the Dynamo environment, and in turn, this flexes the geometry for the tower height, and also the tower floors and podium, and even setback-driven geometry. Levels are defined within the Dynamo environment, and the mass is brought into Revit, where it's possible to generate roofs, walls, and floors from the conceptual study in Dynamo. Here we see the realized form in the Dynamo environment as well as in the Revit environment. Beyond geometric iteration, Dynamo is incredibly useful for automating repetitive tasks that consume countless hours during the design process. In this example, we're automating sheet development and placing views on sheets for the key outcomes of reduced time to design development, increased early stage design profit, and improved design change management. In this example, we can see that there are 39 views in the project browser for levels 1 through 40, and the task at hand is to create sheets for these views and place these views on the sheet. A task that may typically take a team member 30 minutes to an hour may now be completed in 5 minutes with the click of a button and a reusable Dynamo script. As you can see, we've launched Dynamo from the Revit add-ins toolbar, and we have a script ready to go for the task at hand. In this case, we're driving the sheet names and numbers with data from Excel and using some clever filtering in a list to specify the views to place on the sheets. As we run the script, using the manual run process, the Excel sheet opens up, while referenced, and Revit and Dynamo work together in the background to complete the task. With enough time for you to get a coffee, come back to your desk, the run is completed a few minutes later. And we can see in Revit that the sheets have been automatically added to the project, and the views are placed on the sheets. Pretty cool. In this example, by Jacob Small, we're reviewing the automation of placing 8,388 bricks on a curved wall for the key outcomes of reduced time to construction, improved design quality, and improved coordination. This allows us to build up a meaningful digital version of the model as the bricklayer would lay it out on site to optimize the location of control joints and sequencing, and ensure that the brick course is laid out properly or not. Here you can see all of the bricks laid out in the Revit environment. It's really, really impressive what you can do using Dynamo to automate tedious tasks. In this example by Jacob Small, we're automating utility routing by automatically updating the utility line placement and structure on the landscape as the topography changes. This graph actually parametrically builds up support structures, and this results in improved coordination, improved design quality, and a reduction in waste. This example works using both Revit and Civil 3D. As mentioned, when the terrain's updated, the structure that supports lines is also updated. The structure really then informs the routing of the utility and uses the least amount of materials possible. You can see that parameters are adjusted in the inputs portion of the graph, and the geometry is then updated in a visual way in Dynamo's geometry preview. In this example by Jacob Small, we're able to automate the placement of furniture by room type, resulting in advanced propagation of changes in the Revit model. Also, in improved coordination, improved change management, and reduced errors. In this example, we start in Revit and review which room we would like to copy elements from, and make sure that we paste that string into the Dynamo graph. Next, we're also selecting the elements that we want to populate across all of the other rooms in the project. You can see in Revit that the elements are being selected after selecting the Dynamo node for the elements to be selected from. Once all of this is selected, we then go into our Dynamo graph and we're able to run this manually. And when we do that, you'll see that across the entire project, all of these units are updated with the proper furniture. This is an extremely efficient way to make updates, especially for a project typology like multifamily development. In this example by Dieter Vermeulen, Dynamo is used to automate conceptual structural steel designs. This is a Diagrid structure for the Mars Taurus Concert Arena. The geometry in the study is created by minimizing waste, structural weight, and total cost of the structure, including influence of tooling, such as connections, beam cuts, etc. And this results in improved coordination, improved change management, and reduced errors. The variables for the structure are dimensions such as the height of the torus and the division of the diagrid. A business value for a customer utilizing this method of design is that they can generate structural designs that are economic, also lightweighted, and more importantly, cause less steel manufacturing waste. Dynamo allows us to understand design options in a visual way, and the geometry can be studied using sliders within Dynamo and again visualized within Dynamo and Revit. In this example by Jacob Small, Dynamo is used to automate the structure of a curved form in Revit in order to reduce errors in production, reduce time of production, and reduce the overall cost of the system. This is a great example to just show a very practical application of Dynamo in the structural phase of a project for efficiency gains. We're able to select geometry in Revit and run a graph in Dynamo that then automates the structure of a building form even when complex and curvy. This video by Artem Boyko was making rounds on the internet lately, showing an automated process of placing columns, plinths, trusses, and sandwich panels versus a manual process, and had a runtime of 1 minute 10 seconds versus 1 hour 2 minutes. I would recommend running the numbers for time to completion and number of errors on manual processes to get a sense of baseline figures, and then calculate the automated time to completion and multiply by the number of projects in your firm to understand both time savings on a single project and also to understand time savings and ultimately cost savings on your entire company by implementing these processes. The additional benefit of automating tedious tasks is that there will be a reduction in errors from X% to 0%. And this is extremely valuable to note, as we know that small problems upstream can trickle down into larger problems downstream, with major cost implications in the design process. Project Refinery is an Autodesk generative design beta for the architecture, engineering, and construction industry that gives you the power to quickly explore and optimize your Dynamo designs. With Project Refinery, changes and updates to projects become exponentially easier and more time efficient. In this example by Wijnen, we're seeing the optimization of an entire urban neighborhood. Wijnen's a family business in the Netherlands, and they develop a significant amount of properties, including affordable net zero energy housing. After the last downturn, the company was concerned that the 2% profit they're struggling to attain wasn't something that could sustain their business in the long term. Autodesk worked with Wijnen to use generative design technology on a project to explore 15,000 different design options for parcel development. From there, the Wijnen development team focused on the 3 most interesting choices that they could shape into the perfect urban neighborhood. Generative design helped the team to look across multiple dimensions of design all at once. As a result, the designers on the project were able to maximize the amount of solar energy collected to meet their net zero energy goals. They optimized backyard size and views to meet the human needs of their occupants, and they optimized cost and profit to meet the business needs of their company. Here, we're looking at what is commonly referred to as a spider graph in the generative design world. This graph shows the values that are critical to project development, such as views, solar gain, cost, profit, variety, program, and backyard size. The design elements related to the ideals are revealed as the graph advances in the visuals. As the studies run and the designs shift, the results are shown in a way that makes it easy to understand the push and pull between the values involved and ultimately choose the optimal design. In this example, by Daiwa House Group, we're reviewing the optimization of buildings for a site. Daiwa House is a company located in Japan that has been taking an industrialized approach to the craft of designing housing for decades. Today, housing is still one of their core businesses, but they've used an automation and optimization to extend their industrialized approach to condominium and care homes, resorts and retail parks, hotels, and even hospitals. Daiwa House Group uses Autodesk generative design tools to identify the best small developments to build on small pockets of urban land. Designs are optimized based on a variety of factors such as cost, parking, orientation, ROI, and even revenue. Again, we're seeing the utilization of the spider graph to optimize the layout of the site and review the results in relationship to the values that are driving the design. And this leads us to optimal solutions for development. This is an example by DesignTech.io, and we're looking at optimizing the building position on the site. Starting from the selection of a tower mass, the graph here iterates to find the best position within the site boundaries, taking into account the solar incidence and total glazing of the building, resulting in reduced time to glazing analysis and improved sustainable integration in design. We can see the mass in Dynamo, and in this example, Project Refinery is being used to generate options and drill down into the best possible selection by filtering based on solar incidence and glazing performance. To avoid options that don't comply, specifically that are outside of the site boundary, the results are heavily penalized, saving computational time by making the analysis actually fail on purpose. The result of all of this is the optimized building form shown here, and we're actually able to push this data into Revit and continue on with the design. In this example, by the Project Refinery team at Autodesk, we're reviewing the optimization of the building program for a mass in the early stage of design. This study explores the allocation of retail and office space distribution while minimizing cost and maximizing rentable area. And this results in minimizing project cost, maximizing project value per year, and adding demonstrated value through pro forma analysis visualization. This video, shown during the AEC keynote at AU, shows generative design integrated in the Revit environment, showing the ability to run the optimization without entering the visual scripting environment of Dynamo, making generative design processes more mainstream so that more design teams have this supercharged ability to explore the best possible solutions. This example studies massing and programmatic distributions for an urban site. In this example, by Jacob Small, we're reviewing the optimization of a floor plan layout based on proximity and noise ratings and scores. In the space planning graph, we're able to test out thousands of different designs for a floor plan and find the optimal solution. This example starts in Excel, where data for noise and proximity scores are developed and adjusted. This data is then brought into Dynamo, and we're able to make manual adjustments to room layout with the slider option in Dynamo. Project Refinery makes it possible to study hundreds or even thousands of options as necessary, and filter down to the best possible option. Once the final design is chosen, Dynamo automates the creation of room separation lines in Revit, where the design team is then able to keep going with the design. In this process, we have the implementation and automation on the front end, and manual processes on the back end of the design. I really like showing this example because this process highlights the importance of the design team in guiding the project successfully through the design development portion of the timeline, and shows that at certain points in design projects, and for certain building typologies, our crafted approach is still an ideal and completely valid approach to design. The future of design will always require the human hand and human touch to drive visualization, materials, systems innovation, sustainability research, and the subtleties of meeting client needs. In this example by Vermeulen, we're reviewing a crane position optimization that evaluates the imported crane construction elements from Revit through SAT based on their weight and distance to a double tower crane setup. The calculation groups elements per lift status and returns a total lift score for the situation. This results in reduced waste and improved coordination. Building elements such as walls, floors, columns, and beams are imported through SAT, and data references such as crane capacity tables are constructed at the beginning of the graph. The input for the optimization is both crane and truck positions, and the goals are based on lift score as well as time, using the distance of the truck to crane and crane to solid center point as indication of time, and trying to minimize the time that the crane is used for each installation. The resulting options show the scores for the crane positions relative to time and make optimal selections a simple task for the design study. In this example, by Vermeulen, we're reviewing parking layout optimization. We're able to optimize the location of entries and exits, the direction of rows in the layout, the density of the layout itself, the location of payment terminals, and the location and density of electric vehicles, resulting in improved circulation efficiency, reduced time to exit, maximized ROI, and integrated sustainable design. We're looking at the graph in Dynamo that drives the relationships between elements and the visualization of the design. Utilizing Project Refinery, a study is created that allows for optimization of which side the entrance and exit are on, as well as where the points for the positions of those elements are located. Also, which directions the two rows for the lot run in, and also for the density and location of terminals and electric vehicles. Refinery helps the designer sort and filter down to the best possible options. This type of capability development will have a lot of meaning for real estate developers and designers looking to visualize early-stage ideas about site development quickly with trade-off analysis. In this example by The Living, a design studio within Autodesk, we're looking at a very complex method of optimizing an open office layout. The context of this project is that Autodesk moved our Toronto office to a new office in the Mars Innovation District, and the living used a generative design approach to design the new office's space layout. They started by surveying the participants of the existing office, asking them questions like, what groups do you want to sit by? How much distraction can you handle at your desk? Is daylighting important? They boiled all this data down to 6 measurable goals for a good office and created algorithms to measure each goal and develop the design, resulting in reduced time to optimal design discovery and increased employee satisfaction and productivity. Here you can see the process running as different floor plan layouts are created, each with blue amenity bars of meeting rooms and yellow locations of desks. Each design option also involves a dashboard of performance according to its score on the 6 goals. We can see the spider graph revealing score relationships for daylight, distraction, adjacency, views to outside, and interconnectivity. The ultimate takeaway from generative design studies is that we're able to achieve so much more than we were ever capable of by hand. And this is going to give us more time to add more value to projects and extend our services, as well as reduce time on operating costs where those costs are simply unnecessary. With generative design, the outcome of the search and discovery process is completely dependent on the design of the design space, as well as the specification of various measures and search parameters. So, how do you design a good design space? Some things to keep in mind. Values and outcomes are equally as important as the building design itself. And we need to rethink the emphasis we put on value discovery through the integration of a highly involved strategic planning process for all design projects that involves offsites with stakeholders up and downstream for 1 to even several weeks, and places emphasis on how we design the framework of our designs, rather than just completing designs themselves. Outcomes are quickly becoming an integral part of building design vernacular, and it is important that our buildings are designed with performance in mind, and that this performance drives key outcomes for business. What does this mean in practice? Here's a sampling of values related to building design. By no means an explicit list, and open to potentially thousands of additions, depending on the building type and stakeholders involved. Your values are the things that you believe are important in the way you live and work. They should determine your priorities, and deep down, they're probably the measures you use to tell if your life is turning out the way you want it to. For buildings, it's possible to have values in harmony that result in innovative forms, such as this building by Zaha Hadid. And it's also possible to have a very large sample of values that lead to a complex design, such as this academic building. It's also possible to have competing values, even from the same client, that lead to conflicts in design desires and option generation. The earlier the design team can discover something like this, the better. Understanding values at all levels, including of the client, the project team, the local jurisdiction, and even the community surrounding the site, are important to project success, and even more critical in developing design framework. This diagram shows a clear connection between high-level values and the development of design metrics and design elements for a project. Values ultimately inform design goals, and you will not be able to develop a clear framework without them. Outcomes ultimately drive investment, and this is another critical aspect of implementing a generative design process. When money's on the line, the person controlling the funding needs to clearly understand how their investment will bring them a return and what this means for their bottom line. Oftentimes, emerging technologies are put aside because they require an upfront investment, and there's not a clear sense of the business outcomes for adopting these practices. Whether you're a principal in a building design firm, negotiating with a client for higher fees to implement this technology, or you're a part of the design technology team that's looking to compel senior leadership to invest company profits into research, development, and implementation of computational design in an existing project, you should look to the various design outcomes listed throughout this presentation for each workflow to capture an understanding of conveying meaningful outcomes, and also consider these outcomes in the larger context of project strategy. And also think about where your company needs to put in extra effort to be prepared for the next wave of design technology adoption. So, on a high level, to reap the rewards of implementing computational and generative design, you will need to re-envision strategically how you design buildings, expanding your scope of services and integrating technology for increased efficiency. Here's a diagram showing steps for redefining project strategy. An interesting part of this diagram is that the future of building design will most likely expand training of your staff in areas such as strategic planning, coding, data analysis, manufacturing, and customer success. In this diagram, you can review steps to implement computational and generative design in emerging projects in your company. The main point I would like to make here is that for this type of design to take off successfully, you really need to fund the right project, staff, and client. Those that are willing to forge through new frontiers of design with a new design methodology. Also those that are interested in high levels of communication and collaboration and will not shy away from giving input at the outset of a project. Also those that are willing to listen to input from all levels of stakeholders upstream and downstream in a project. Aligning these personality types at the outset is tricky, but invaluable to project success. Beyond identifying the right teams, identifying the right project for implementation is an interesting opportunity or challenge. You need to consider the difficulty of implementation in terms of cost and also the impact of investing in terms of importance. Many computational design process automation graphs will fall into the category of lower difficulty and higher ROI. Most generative design studies will at first fall into higher levels of difficulty and high impact as long-term investments. But over time, the studies will become easier to develop and implement, bringing them also into the high ROI category as well. At this point in time, I don't see many automation or optimization projects that are of low importance for the building design industry. So at this point, luxury items or easy wins are going to be less common. When you're looking to get started, here's more information for you about Dynamo. Dynamo is currently integrating with Revit, Civil 3D, Advanced Steel, Alias, and Format. 2020 global launch has continued to solidify Dynamo as a common language shared across and beyond the AC portfolio. Moving from the single to multiple hero products demonstrates our commitment to end-user programming and reinforces our commitment to focus on Dynamo's development as a reliable component technology. Here's more information about Project Refinery. This tool is used to explore and optimize designs, and is currently available from within the Dynamo for Revit application. It's possible to sync results discovered in Refinery back into Dynamo and then push them to Revit. You can sign up for the Refinery beta today and start testing. Here are some additional resources to help you get oriented to working on graphs in Dynamo. And if you enjoy the community aspects of group learning, there are active Dynamo user groups all over the world. For example, in Atlanta, Boston, Shanghai, Ireland, the Netherlands, even Madrid. You can find your local Dynamo user group at dynamobim.org/a world of user groups. Once you have staff in place to work on computational and generative design projects, I would recommend investing in their problem-solving development by providing them learning opportunities at residencies and hackathons. These types of events give developers exposure to high-level approaches to problem solving by their peers and reveal new methods for implementation, such as using bin packing algorithms to solve spatial layout problems. Here is a handy checklist for you to use when implementing outcome-driven design in your company. I'd recommend handing this off to an executive involved in operations so that they can have a sense of the scope of work needed to organize the company around the new design strategy process. Here's a sample list of opportunities for process automation with computational design. And a sample list of opportunities for design optimization with generative design. At your next offsite with your executive team, consider what these opportunities could be for your firm. In conclusion, implementing computational and generative design in your projects will require a shift in strategy and possibly, more importantly, a shift in mindset that heightens the discovery of values and outcomes. So, after you've automated out the tedium from your processes, where will you go next? Experience research? Sustainability research? How about resiliency research? I look forward to seeing what you will develop in your projects moving forward. And when it comes to making the world a better place, I believe in you. Good luck, and thank you so much for your time.